so today's topic again deals with the idea of what is a rate, how do we calculate that, and there are three main portions to it: calculating using a formula, calculating using a graph, and then finally calculating based on the data table collected. So that's the overall kind of overview of this topic. The first thing we should discuss is the idea of rate order. There are three main types of rate order. Certain reactions are considered zero order reaction. Others are considered first and then second order. I should point out there are more, but for year one chem, these are the three we're focusing on. The way these three reactions, or the way these three types of rate order work, the best way for us to understand them is by using an example. So I'm going to write on screen real quick. We expand this, move it over to the side. If we're dealing with a zero order reaction, the way we can do this is by using numbers. So rate is the speed of the reaction. K is a constant. And for right now, we don't know that yet, or we don't know a number yet, but it's something we can, we're going to find out towards the end of this discussion. X is the concentration. How much of the reactant are we dealing with? And then finally, since this is considered zero order, it's raised to the power of 0. So if I have, I'm going to use some numbers here. I'll say R is our rate. Annotate this. Give me a second. Drawing. So if R is represented, or if R is our rate, K is again our constant. And let's say our X is 1. If our X is 1, but it's raised to the power of 0, isn't the answer in math, any number raised to the power of 0 is 1. So if that's the case, can't we conclude that R must be K? 1 raised to the power of 0 is just 1, so 1 times K is K. This tells us that R is equals to, or it's going to be equivalent to the constant of that reaction. On the left, it says, what if the concentration is doubled? So what if we double this concentration? So let's try that out. So now if our K is still the same, what if our X, the concentration, is now 2, from 1 to 2, it's doubling, but it's still raised to the power of 0. Isn't our answer R is equal to A fill? Can't we conclude that certain, for zero order reactions, for chemical reactions that fall in this category, the rate is always the same, or the rate is constant? A way to visualize, or conceptually, what it means is that there's some reactions where it doesn't matter if I double the amount of stuff I'm using, the reactants. How fast I'm making the product will not be affected by it. So it will just keep going through the reaction the same exact rate, the same exact speed. So those reactions are considered zero order reaction. Now let's take a look at first order. Based on how the formula is written, rate is equal to Kx, but because it's first order, it's now raised to the power of 1. So let's do the same setup. Let me try to draw a line here. If our rate is equal to K1 to the first power, so I'm using our kind of a way for us to make sense of this by using numbers. What if our X is 1? Then wouldn't it look like this? So now, based on that calculation, 1 to the first power is just 1. R must be equal to K. Now let's try the second portion of this scenario, because it says again on the left, if the concentration is doubled, what will happen to the rate? How would the speed of the reaction be affected? So let's try that. R is equal to K, and then 2 to the first power. So now all I did is I doubled the amount of our X value of our reactant, and 2 to the first power is 2. So this is R is equal to K. So compared to zero order, where it doesn't change, first order it does change. But the way it works is that the rate, if we double the concentration, the rate is also doubling, which means the change in rate is directly connected or related to the change in concentration. So I guess a way to paraphrase would be if x is doubled, let's see if I can try to fit all of this. If x is doubled, then rate is also doubled. Or if x is tripled, the rate will also triple. If x is quadrupled, the rate is also quadrupled. So they always match each other. So that would be an example of a first order reaction. Conceptually, what that means again is that there are some reactions where if I change the amount by a certain factor, the speed of the reaction is going to change exactly the same way. So if I double the amount, I double the speed. That's the idea of first order reaction. Now let's try the last one, the second order reaction. Rate is equals to kx to the second power. So same approach. I'm going to use 1 as our starting number. R is equal to k, sorry, it's supposed to be 1, eraser. 1, but this time it's raised to the second power. But since we're dealing with 1 squared, it's still 1, right? So our answer is still R is equal to k. What if we double this now? So R is equal to k 2 to the second power. If we do that, aren't we going to end up with a value of R is equal to 4k? Let me write this down. Meaning 2 squared is 4. 4 times k is 4k. Now with this, let me try to draw a line to separate this, kind of running here. But can't we conclude that the rate is exponentially changing? And it's always going to be the square of the change in their concentration. So to repeat that, or to kind of paraphrase it, if I double the concentration, the rate is now 4 times. If I triple the concentration, 3 squared is 9. So now the rate or the speed of the reaction is now 9 times as fast. So there's this exponential change in the rate of the reaction based on the change that we're doing to the concentration of our reactant. I know it's a bit messy on the screen, but on the next page, I have kind of just their abbreviation or the summary of the main idea. So let me show that real quick. Let me clear this mess first. And here is the summary of the key points. The idea again here is that there are 3 types of 3 main types. There are more, but these are the 3 main. Chemical reactions that are considered 0 order, chemical reactions that are considered first, and then chemical reactions that are considered second order. To 0 order reactions, the speed of the reaction does not change, consistent all throughout from beginning to end. First order reaction, the speed of the reaction could change depending on what we're doing to the reactants. If we're doubling the reactants, the speed will double. If we triple the reactants, the speed will triple. So they're constantly matching each other. Now the second order is different because the change to the rate is exponentially or exponential compared to the change in our concentration. So if you double the reaction, you quadruple the speed. If you triple the reaction, it is now 9 times more. If it's, let's say, 4 times 4x, then isn't that 4 squared? So it's 16 times more in terms of the speed of the reaction. I'm going to pause the recording to allow you to ask for a question. First, let me, I don't know if I could pause the recording and pause the stop sharing. I guess I have to stop share. And then, all right, so we have, again, there are 3 types of rate order, 0, first, and second, but how do we know which one? And the way we're gonna go about it is 2 different, there are 2 ways that we can go about it. First, I'm gonna mute everyone, I forgot to do that step. I'm hearing a lot of background.